Alrighty, my friends. What do I got here? What do I got?
But you guys start with this week's data structures.
Yes, the instructions are pretty good, and I've emailed him twice. Have you? It's not too bad if you copy the book class for most of it.
What kind of stuff is it asking for?
Basically the same as far as I can tell, easier to learn.
All right, my friends.
So, hopefully you got the email. 2 parts today. It's our short day of the week, so that's always lovely. I want to maybe get your attention for the first 10-15 minutes, and then we'll get on to the web work. But I want to show you a couple of techniques that we didn't get a chance to talk about. One little detail. Cool, so if everybody could shut their laptops for a few minutes, unless you're doing notes, and then that is completely kosher. And then when we're doing the web work, ask questions and we can deal with them as a group. So we're talking about integration by parts. And there's one important thing we didn't get to talk about. So that would be in the instance where I have something like this. The integral from 0 to 1 of x e to the negative x dx. So we didn't do definite integrals. And I just wanted to talk about that, give you my advice on it. There's multiple ways to do this, but I think there's one best way. That's my personal opinion. So, let's start from ground zero. I gave you an integral. You look at the integral. Your first plan is, what kind of an integral is it? In other words, what is my approach going to be in tackling this thing? So you could try substitution. That would fail pretty badly no matter how you did it. But when I read it, it says x times e to the negative x. And remember, and I strongly recommend reading the things in your head and saying the numerical operations. Because I'll come around and I'll help you and you'll be like, I don't know what to do on this one, and I'll say, read it to me. And then you'll say it and you go, oh, times. So times means parts is probably what I want to use. Not always, but it's a good first step if substitution fails, as it would here. So I'm going to let you be the thing that gets simpler when I differentiate it. X goes to 1, e to the negative x goes to negative e to the negative x, and then that goes to e to the negative x on the next differentiation. So this stays the same complexity, but this gets simpler. So I'm going to let u equal the x part. And then dv is everything else. Between these two things, u and dv, everything must be accounted for in the integral. So this is the setup. Then it becomes a routine. So this is initialize the algorithm, perform the algorithm. So derivative of x is 1. I tack on dx. To get v, I take the antiderivative, and I remove the dx. Notice here I lose the dx, here I gain a dx. Then I go to this formula. The whole point of this was to write this integral that's in u dv form as uv minus integral v du. So I'm going to actually put the definite form of this up here. If you had limits right here, carry those limits across. This bar just means I'm going to evaluate this at b and a and subtract, and then I rewrite my definite integral here. So that's the form I'm going to use. Right now I've got this. So for us, this is going to equal, so in this case, this is going to equal x times negative e to the negative x from 0 to 1 minus integral from 0 to 1. V is negative e to the negative x, du is dx. And this becomes, now I can just plug stuff in. So when I plug in the 1, this becomes negative 1 times, well, this becomes 1 times negative e to the negative first. So let me write this out and tell me if that makes sense. So that's when I plug in the 1. So plug in x equals 1. Make sure you're cool with that. And then minus, I'm going to plug in x equals 0, and good shit, this dies off. And I'll write it out just so that we have it. Plug in x equals 0. So that's this. And then minus, now I've got this other integral. Check it out though, I'm gonna do a quick rewrite. There's a minus minus. Simplify along the way to minimize suffering. And let me stop for a second. Because I just came in here and started cranking. Does this look good? Any questions? Yes, Sophie.
The only question I have is I was looking at the webwork, and there are some cases where like you have to take the antiderivative and you also have to do substitution, so that can happen, right?
Yeah, we'll take a look. Yeah, that totally can happen.
Okay.
Yeah, we're starting out chill here today, but I'll be happy to talk about one like that.
All right.
Yeah, you betcha. Any other questions? Okay, so then we carry this up, and then this is just going to be negative e to the negative first. I don't need to write the 0 part, but I am just going to go ahead and crank this out. Antiderivative of e to the negative x is negative e to the negative x. And I'm just saying that. Does anyone need me to explain how I moved from this to that? And I should put a plus here, sorry. Any of, no, they're good.
Yeah, can you explain it?
Yeah, absolutely. Yeah, you got it. So let's just look at this on its own really quick. So what I did here was I realized that I really just needed this, and that's this form here. I'm actually going to give you some quick, I'm glad you asked, because I'm going to give you guys some nice little quick rules. So this, do you see that that's the form we have?
Mm-hmm.
So that would mean u is negative x, du would be negative dx, and I'm kind of going against my rules here. I changed it to u, and then didn't change the limits. It's okay. I just kind of really want you to see how fast this can be. So then this becomes dx is replaced with negative du. That's going to be, I'm going to replace that with negative du. I'm going to replace this with u. So this is integral e to the u negative du. And that's negative e to the u du. And then the form I'm just going to use it. So that would be just that little piece there. I'm going to keep the plus, bless you, keep the plus c off, back substitute. So that's kind of what I did. But here I would put these following forms on your sheet and have these at your ready. Really great quick rules because they show up all the time. And then we'll finish the problem. But these are fast substitution rules for things that appear all the time. So if I have integral of e to a constant times x, you'll see that a billion times in this class. That's just 1 over k e to the kx. You can just go right to that. If I have integral of sine of kx, that is negative 1 over k cosine of kx. And then finally, let's put one more up here. That's equal to 1 over k sine of kx. So really, like, have your integral sheet by you when you're working, but have these maybe right on top because literally they're the most common forms you'll see all semester. So in that case, I could have just looked at this one and realized k was negative 1 in this, right? And then I go, oh, okay, so that's just negative 1 over 1 e to the negative x from 0 to 1. And it's a lot faster, right? You don't have to do all this nonsense. It's not nonsense, it's just a little bit of overkill. So then this one I gotta finish it up. This is gonna be negative e to the negative 1 plus, now use parentheses and braces and stuff to keep yourself safe. Plug in the 1, plug in the 0. Notice I'm subtracting e to the 0. Parentheses are your friends. Never worry about using too many. Using too few is the problem people have. So this is this. E to the 0 is 1. So that's my final answer on that one. The other route is to pretend there's no limits on it, do integration by parts, no substitution, and then come back at the end and plug in 0 and 1 to your answer. I think it's wiser to do it like this. Any questions on that? Let me pick up this shit that fell out of my bag.
Shouldn't it be 1 minus e to the negative 1? 2 e to the negative.
Yes, thank you. Good call. Yep. There's 2 of those. Yeah, beautiful. Oh, I got the 2 in the wrong place. Thanks. Yeah, got a little excited. Great, that's an excellent question. Thanks, Warren. Any other questions on that? I've got one more thing I want to show you. Okay. So, on the webwork, so I made some suggestions on which ones to do first. Because I was trying to keep you away from this one. Let's say we have something like this. And Sophie, this is actually going to kind of address your question too about substitution required in parts. Okay, look at the problem. I think, what method am I going to approach this with? And you know it's parts because that's what we're doing today, but if you read it, it's x squared times sine of 2x. I can do the x squared easily on its own. I can do that easily on its own with a little substitution or the new rules I showed you. So I've got a product of 2 things that are sweet, but I can't do them as a product. So I want to show you a fast, So we would go through, let u be the thing that became simpler. And then I'd have to do du is 2x dx and v. Now I can use those quick rules. Remember this rule that I just had up there?
Is the sign du or dv?
Hold on a second, let me get this up. Is the sign is dv.
Okay.
Because so I let u be the x squared because it'll become simpler, and the sign kind of always stays sine or cosine, it never gets simpler. So check it out how fast I can actually do that with those rules. Here I have k is 2, so it's just, and this should be, there's a negative in front, so this is just negative 1/2 cos 2x. Boom, I don't have to use substitution, it's in the rule. So then we go through and we write uv minus integral v to u is our next step. And so that is going to become uv is negative, I pulled the 1/2 out in front and the negative. And then I put plus or minus integral v to u, so check out what that's going to be. The net effect of the negative half and the 2 becomes a negative 1. That is going to become a negative 1 I bring out front and turns that into a positive. So I'm getting a little bit more sophisticated as we go through. Make sure you see that. And you feel good, and that I'm right. Like if you're catching errors, please let us know. Does everybody see? Because there was a minus here from the formula. There's a minus here, so that became a plus. The 1/2 and the 2 make up 1. It's nice and pretty. How would I do this? Same thing. This is parts again, right? So to do this, it's x times cosine of 2x. This requires parts again. Are you shitting me? I gotta do parts again? I am not. I shit thee not. this requires parts twice. So and this is going to happen, especially, imagine if I had an x cubed here. I would have to do parts 3 times. X to the 5th, 5 times. That could be a real mess. That requires a lot of parentheses. So what I want to show you is a great way to organize this whole process. You can do integration by parts this way too. So we're not going to finish that way because we have a better way to do it. So here's my old thing. This requires parts multiple times. Better approach is called tabular integration. This is the big thing that I really wanted to show you for today. So, tabular integration, you're going to make a table. It's going to have 3 columns. It's going to have a sign column, S-I-G-N, it's going to be plus, minus, plus, minus. You're going to have a differentiate column, and you're going to have an integrate column. And you're going to initialize this table. So the first row is you initialize it. And what you initialize it with is you always put a plus here. Here you put what would be u, so kind of put in parentheses. This is where the u would go. It's the thing that gets simpler. So this column should get simpler with repeated differentiation. And then the integrate columns, everything else, you don't even need to tack the dx on. So that's going to be sine of 2x. dx if we were doing this with our traditional notation. Let me stop for a second. Yes, Sophie. Yeah.
So you're not pulling that from the second part of the equation, you're pulling that from the first part?
Yes, let me get rid of all this shit. In fact, stop that potential confusion. So this is from the original problem. Yes, thank you for making sure that's clear. So here's how you rock this out. You're gonna love this, and you're gonna love having these formulas around. Let me get the other one that we're gonna need in just a second. So take this column, the U column, the middle column, and differentiate until you hit 0. Each new level of differentiation becomes a row. And now I can stop. Just take derivatives until you hit 0. On the sign column, put alternating signs all the way down. You don't really need this last one, but until you get what's going to go on here, just plus minus all the way down. Over here, I integrate all the way down to whatever the 0 level is. That's why these are going to make life easy. So this next one, antiderivative of sine 2x is -1/2 cos 2x. Antiderivative of cos 2x is 1/2 sine of 2x. There's already a -1/2 out in front. Let me stop. And I would like you to make sure you understand what's happening in that right-hand column. Really important. Because if you do, you've got this. But if you don't, we need to talk about it. It's also tea time. A little bit of tea. And then I ask you, just take a minute. Can you fill in the last entry? What should the last entry be in that column? got positive 1/8 of cosine of 2x, you rocked it. And if not, ask. Let's talk. Good. Awesome. Yes.
Why do we need the sign column?
You'll see. Because we're not done. We're gonna weave this stuff together, and those sign changes are really gonna become important. And the reason they're even there is, remember what the main formula is like? You got this minus. So every time you do another parts, another minus gets mixed in. And so it works out to balance things for us. You're really gonna love this, I think. I think you're gonna be really happy that you learned this on a Friday. Because this is perfect weekend fun. So the next thing to do is now we're gonna weave these together. So you make these lines, you move straight across the, oh, I wanted blue. How did that not work out? Straight across and down. Straight across and down. Straight across and down. And I don't need to go straight across here, because what I'm gonna do is multiply along these lines. Multiply. And this one will have a 0 in it. And multiply. So this first one is going to turn into plus x squared times -1/2 cos 2x. This one's going to be negative, let's just put the whole thing here so that we see it, -2x times negative, excuse me, 1/4 sine of 2x. And then my last one is plus 2 times 1/8 cosine of 2x. So you multiply, and it's weird, you just gotta get used to it and have an example by, so that you see what I'm doing. I'm not even using this guy here, but I am using that. And I'm not using this doesn't get used. Everybody good on that? Because that's the hard part. Now add those together and you've just integrated. So add these up. And what we get is, and I'll do a little simplification, this is going to be -1/2. I like constants in front, you should like that too. That's just good math etiquette. This becomes negative, so the result is a positive. 2 times 1/4 is 1/2. So plus 1/2 x sine of 2x. And then plus 1/4 cos 2x. And now I'll tack on my plus c. And I'm done. Isn't that sweet? And you don't have to like keep all these nested parentheses with multiple, yes, Alice, yeah.
Why is the 1/2 x sine 2x positive?
This guy right here?
Yes.
Cool. So I had this negative from here, and then that balanced with this negative. Does that make sense?
Yep.
Cool. Awesome. Let's practice one together. Let me give you one. And when you see this, you might think, oh, that bastard. I hope you never actually think that about me. I hope I never do anything to be thought of as a bastard. So let's see. So I would like you to do, you can see, bastard move to do that x cubed, but that's okay because you have the power. And then you're going to want this. This will be an incredible friend to you. Kx. So let's make sure we set up the table right. You don't even have to put these titles on here once you know, but let's do it for today. Plus, what am I going to put in the middle column? X cubed, because that will become simpler. This will never get simpler. All right, go forth. See, now you just integrate at a speed you never knew was possible by hand. rest of the class to work on the webbook. Or a pen cap close or something, it's like locked it in. Whoa. Ooh, wow. Not good. There we go. Better. Apparently my lines aren't drawing very well. Put it in a line. That's your antiderivative that you had to roll. It's kind of cool. Like, really powerful. You can actually even use this for regular parts if you want. You can do it even if there's just once you want to do it. It'll work out for you. Yeah, smile, smiles. That's good. Yeah. This is a happy day. It's a great day. Any questions at all I can answer on that, my friends? Make sure all, yes.
So if instead of like x cubed times e squared to the x, if it was something like sine 2x or something, does that just go on forever?
Oh, if it was this?
Yeah.
Yeah, that's a tricky one. I'll talk about that on Monday.
Okay.
Does that sound okay? Yeah, 'cause if both parts repeat, there's a little trick to getting it to work, but we kind of got enough on our plates right now. But what an awesome, I'm glad you're thinking like that. Yeah.
Well, if we were to do this on the test, would just this final long equation be acceptable, or would we need to simplify?
Kind of an A student question is that?
Yes.
That's an A student question. I love that. Like, first off, on tests, I just want you to get the right answer, you know. But if I was, I like the gusto that shows. It shows all different kinds of gustos. You could pull the e to the 2x out of all of it, and you could do this. And there's some elegance to the, ooh, and I could make that 3/4, right? X, and I could make that 3/8. And then I could do that. So something like that would be like really the only other next move, but it's got its charms.
Okay.
Thank
We
you.
don't have to?
You don't have to unless it says to.
Okay.
Yeah. But I would probably never ask you to do that move.
Cool.
So you're good to go.
How do we know when to use this type of differentiation?
When, you mean this table method?
Yeah.
Yeah, so, anytime you recognize there's parts and you see a power of x that's more than 1, this is gonna kick in. Even though I could do it on a single integration by parts. So let's say I had integral of x cosine of 3x dx. I can do it here too. So we got the sine. It almost takes longer to write this whole damn table out than to do parts, but so this is my diff, this is my int. So then I set up, I put x here, I put cos 3x here, I put, now I just populate, right? So 1, 0, and then this becomes 1/3 sine of 3x. See how nice it is to know that form? 1/9 cos 3x. And then Sophia, I could just like go, so you can almost always use this and get your answer out. Yeah. So if you like this, if this helps your brain, if this helps organize the information better, rock it. And then if there were, had there been, God help us, like limits on this thing, I would just do this all and then slap them on here, and then just do it there.
Okay.
There might be another surprise somewhere in the web work that someone will need to ask me about. I'll let you find it. A little golden egg in there. There goes, yeah, Becky.
Oh, where did you get the -3/2?
The -3, that's a good question.
Should be fourths, shouldn't it?
Should be fourths. Thank you. Yeah, thank you. Excellent question. I didn't copy properly in my spasticity. So, Gabe, did you have a question?
That was a.
Okay, yes.
I think you tried to pull that 1/2 out in front because everything else is off by 1/2.
Maybe. I really love that you're trying to figure out that I tried to do something good. I appreciate that. I think it was just a half-assed copy.
Fair enough.
But yeah. But you could pull a nice 1/2 out too. I like that. Yeah. Other questions or ego boosts for me, things to help me feel better? Always looking for them. Okay, cool. Work start on your web work. Or if you are, continue with your web work, and then as you have questions, let's talk. There's no new homework for Monday. That's it. I'm gonna run to the restroom real quick. It's always plus minus,
Okay.
yeah. That sign column always rolls that way. It always starts plus and then alternates. You got a question on something?
I just can't remember the equation for integration by parts. Isn't this supposed to be an equals? Yeah, thank you. You're welcome. Look, you don't have to look shit up on the web. I would be able to easily find it.
Okay, no. You're welcome to.
Can I talk about, this is a great one, this, I think you found the egg. All right, Abraham found the egg. You want to talk about it?
Good. Just looking forward to this moment. Let's say we had something like this. We'll make it a little different. So I think you have like a square root of t. I know Abraham does, a square root of t. If you had a square root of t, I would still remember convert that to t to the 1/2. So this is one of the special cases when you're integrating by parts. So if I let you, and maybe you'll feel different about this, I always want you to be the thing that becomes simpler. The derivative of t to the 3/2 with respect to t is 3/2 t to the 1/2. That starts to feel like it's getting simpler, and then next derivative would be -1/2 exponent. But the derivative of natural log becomes 1/t. I don't know, does that feel like that became simpler? Does that, okay, cool. I guess it doesn't have the log in it, right? Anytime we're getting rid of logs, life is better. So for this one, the trick, anytime you see a natural log in there, the trick is to let u be the log part let's just finish this up real quick together, and then t to the 3/2. This is gonna get more complicated exponent-wise, but the whole thing's gonna work out real nice. So then power rule here, that goes to 2/5 t to the 5/2 dt. And so when I put this all together, let me actually just wrap this one up. So uv is going to be 2/5 t to the 5/2 log t from 1 to e. And then I'm gonna have minus integral 1 to e v du, so I got a 2/5. Notice how this t here knocks off a power here. T to the 5/2 divided by t is t to the 3/2. See what's going on there? T to the 5/2 over t equals t to the 3/2. So then I knock this out. Let's see, natural log of e is 1. Wait, what the hell is in front here? What is that? Should that have been that's a 5. It should have been, I wrote it backwards. So this should be 2/5 e to the 5/2 times 1. Natural log of 1 is 0, yay. 2/5. This goes up to t to the 5/2. And then I'm gonna do that from 1 to e. And so I'm almost done here. 2/5 e to the 5/2 minus 4/25 t to the, be careful here, put this all in parentheses, e to the 5/2 minus 4/25 times 1, and then that's, you can simplify from there or not. Make sure that's all looking good, make sure it's legit. Yeah, on a test, if I was worried about it like on a test, I would make this prettier. If I had some time, I would do this actual subtraction. This is 10/25 minus 4/25 is 6/25 e to the 5/2, and then the minus becomes a plus 4/25. So that you can't really do much more than that. That does look better. Don't ever get calculators out to do this stuff. Just my tip. Yes, Sophie?
Can you explain how you went from t to the 5/2 to e to the 5/2?
From here to here?
No, on the left side.
Oh, here.
Yeah.
Cool. So this is the UV part, and I'm evaluating that from 1 to e, so that's what this means here. So I plugged in the e, and I got 2/5 e to the 5/2. Natural log of e is 1. And that might be what you're missing. And then when I plug in the 1, I get 2/5, 1 to the 5/2, natural log of 1, which is 0.
Okay. So you just plugged in the integral there.
Yes.
Okay, got it.
Yeah. Oh, yeah, I've never seen that, yeah. So this is, use acronym, log, what does the I stand for? Inverse trig, polynomial. Exponential trig. Oh, that's cool. Yeah, that all looks legit. Yeah, I wanna make sure that I was right on that. Yeah, yeah.
I don't remember this as much as I thought I did. Separated them out into this form. And it looks like this integral, I still have 2 separate parts with an x. So I don't know why I integrate that.
So hold on, okay, so that's me. Just move this over just a little bit. Okay, so here's what we started with, right? And then what's this here that you rewrote?
This.
Well, this is that. Oh. That's what you started with. So here's the thing you're given, and then we convert into that form.
Makes a lot more sense.
Does that make sense? So, but there's something missing here, so let's check it out. So let's organize some things just a little bit more, because I would keep this in like a table of some kind, just for your mind's sake. So if you put u equals x, and you want to put v underneath, that's all good. And actually, this should be dv. So the thing, right? So I pick u and dv, these are the things I choose. And then I would either go across, or if you're doing it across to begin with, go down. du is dx. And then here v is, now you got their 130 to the 3x. And it just makes it a little, you know, like easier on your mind. And then you plug into that. Cool, yeah.
Took it out?
Awesome, that's great, good to hear.
You have something you wanna talk about?
Okay. I was getting the sense that maybe we wanted to talk about some. Okay, outstanding.
Thank you.
Sorry, I'm just always looking, you know.
E to the negative one is one over E, right?
Say it again?
E to the negative one is one over E.
Yeah, it is.
Which is cool.
And then just a negative, if the negative is then you can just tack that on, that doesn't have any bearing. Cool.
Doing okay.
Oh, yeah, that's great. I'm glad to hear that. I have a sister that goes here too.
Mm-hmm.
Is her name Bridget?
Yeah.
Okay. Okay, I was wondering, all right. I was like, what's h of t? That's your log, okay. Okay. UV. Looks great. Yeah, here's what I went wrong. So you already had this 4/3 out in front, and then you raised that up to 2/3. And you multiplied front by 3. Wait, yeah, because a triple raised that up by Yes, yes, 3 halves, so then when I take the 3 halves and I multiply by 2/3 out in front.
Oh, it's by 2/3.
Yeah, does that make sense? So you're missing a 3 in the bottom there, yeah, yeah.
Wait, hold on, I thought I did that though. Because I tried to get that down.
Well, what's 4/3 times 3, 2/3?
There's 2/3, that was, oh, was it 8 and 9?
Yeah. That's what I'm saying, yeah, yeah.
Okay.
Okay, take a look here real quick. Yep, looks good. Great. Oh, this should be an integral. At least it should be written that way, so this should. Oh, okay, I see it, okay, got it. Oh, I see what you did, okay, so I need to do that, so. It was 2/3. So that was just, right, okay. You're actually. What did you multiply by in front? So you already had the 2/3 out in front. When you up this by 1, you get 3 halves. You need another 2/3 out in front. That's right. Okay, well, let's take a look together.
So first thing I did was get the 6.
Yeah, good move. And then you converted that to 1/2, so this all looks nice. Except you are differentiating here, not integrating.
Okay.
Does that make sense? So, check it out. You can see it better this way. But that should have, you should have added 1 to the exponent instead of subtracting. Yeah. Okay. And then, careful, what comes out in front, I can't tell what you wrote there.
3 halves.
1/3 halves, 2/3.
Okay.
Yeah?
Yeah.
There you go, all right. At least you're on the right track. All right, friends, I can't hang too late today. I got someone coming by my office hours. Some of you might even have class, I'm not sure. But this isn't due till when? Can you see when this is due?
23rd,
What day is that?
Monday.
Monday? Yeah, okay, we can maybe move it to Tuesday, but like try to get as much done by Monday as possible, and then come in with questions to clean up whatever you got. And that'll be great, and I'll see you on Monday. Thank you.